Chiral molecules can exhibit differences in many ways regarding handedness. That is directly the way they affect human beings. For example, a compound called limonene gives an odor of simply oranges, whereas its other enantiomer it gives the odor of lemons. So likewise, same carbon gives essence of caraway, whereas its other enantiomer it gives the essence of or flavor of spearmint. I'm Professor Dr. Mchem from Dr.Mchem Institute of Chemistry, University of St. Jamshedpur, and I'm here again with something very interesting and a new topic for you people to understand that why do we call a compound or why do we designate R and S configurations to a compound, right? A single compound that has got the two configurations, that is R and S. We call it R and S. What is this R and S? Let's discuss that. Now, regarding the drugs we are talking about that has the enantiomeric forms, that R and S forms, they they were sometimes years back ago, a decade ago, they were some of the drugs, they were responsible for some, major, the reason of major drastic consequences faced by different human beings. Like, for example, a drug named as thalidomide or thalidomide was given to the women who were conceiving, that is the pregnant woman, to control the morning sickness. But with the passage of time and with more and more discoveries and more studies on that drug, it was found out that one enantiomer of the drug was because after giving that drug, the patients were having some side effects, like the newborn kids were coming up with birth defects, major birth defects. So now definitely the drug was under consideration for that what is happening, why is it so now what happened, that one enantiomer of that thalidomide was responsible for curing that morning sickness, and that was the right enantiomer, that is the R enantiomer, that is the right. R stands for rectus, and it's simply is called R, right? And it was actually the enantiomer that was responsible to control the morning sickness, whereas the other enantiomer in the same drug in the equal amounts, that is the other one, the S enantiomer, it was responsible for those birth defects that were coming up in that were found in different time in newborn babies. So it was quite difficult at that time to provide the evidence against these regarding these side effects. So this was because both of these enantiomeric forms were interconverted. So definitely you can simply see that how difficult it was to find out in those days that if a drug is given to patients and they are coming up with such a when the babies are coming up with such a problems, such a major defects, it was because of the one enantiomer and both enantiomers were in the equal amounts, were present in the equal amounts of the drug, but one was causing the positive effect on the patient, whereas the other one was giving the reverse of it, that means the birth defects. And as they were interconverted, so it was difficult to provide evidence against these two enantiomers. So now later on, so we have now a little this was something little information I've given you regarding these enantiomeric forms, that is R and S forms, whereas now R and S are both simply you can see what is this R and S. What is R and S? So R simply is, these are all the Latin words, right? And R is for simply rectus, and S is for Sinister. R stands for right, and Sinister is for left. That is, R and S means right and left. So enantiomers, right? So this is something might have seen in many of compounds. They have their name there with their names. It's written RS2-butanol, R2-butanol, S2-butanol, like this. In the brackets, R and S designations are given to the compounds. So what are those? These are the things which I've just explained it to you, that these are the two. R and S are the Latin words. Up till now we have understood this, and they are simply called the rectus and the Sinister, and that is right and left enantiomer. So this is the basic information which I've given you just now. Now these RNS that is having the opposite configurations at carbon number 2. So now we will consider the case of R2-butanol and S2-butanol now in our this section, and I will explain you how you can assign them R and S designations, and on what basis we assign them these. This molecule is given an R configuration and S configuration to any molecule, but we will give you the example of a 2-butanol molecule, because this is something very simple and very easy to understand, and it's you've been going through this compound since many of my lectures, so I took the same example for this typical topic also, so that that would be helpful for you to understand the RNS configurations. So as I was discussing today, our topic is nomenclature of enantiomers, the R and S systems, right? So basically I was telling you about the R and S systems, what R stands for, what S stands for, and now in my mind I have a 2-butanol molecule which I have prepared again. It's a beautiful 2-butanol molecule. You can see its shape and how it the connectivities, right? So this is an oxygen atom and this is a methyl group. This is simply a carbon atom with the 3 hydrogens at the top, and then of course a carbon and a hydrogen, and then this you can turn it over, COH, simply COH, right? And then yes, this is again a CH2 molecule and CH3. This is an ethyl group. Basically this is an ethyl group over here, an ethyl group, and then of course an OH, CH, and methyl group at the top. So this is the basically a molecule, a 2-butanol molecule, right? So now I have this thing in my mind. Now today we are going to discuss the nomenclature. So as I mentioned that R and S, these stands for R and S. These stands for rectus and sinister, SINISTER, sinister or sinister, right? And that is, of course, what does that mean? Right and left. Right and left, right? So if somebody asks you what is R and S, you simply say these are the Latin words, Latin language, and so they are simply termed as rectus and sinister, right? And or R and S forms, right? This is it. So now let's follow what are the RS and S forms by the following few rules. Now I will draw this 2-butanol molecule over here so that you can easily see how to designate different positions and how to give the priorities. So let's make the 2-butanol molecule. So that you can easily memorize, or you can simply see that how these would be. CH2 and CH3. So now, first of all, this is enantiomer of 2-butanol enantiomer. This is a 2-butanol enantiomer. So now here simply you see, first of all, what you are going to see, you are going to look for the stereogenic carbon. Where is the stereogenic carbon in this whole molecule? Where is the stereogenic carbon? You have to find out first. So this is the stereogenic carbon. So we are going to give an asterisk to this so that you can see this is a stereogenic carbon to which these 4 groups are attached. That is a methyl group, a OH, H, and an ethyl group, right? Ethyl, hydrogen, methyl, and OH group. Now there are 4 groups attached to this stereogenic carbon, right? This one, the stereogenic carbon. So now these groups are attached to the stereocenter. Now this is also called a stereocenter or stereogenic center, stereocenter or a stereocenter. So now these groups will be given priorities, okay? Like now, as I've mentioned that these 4 groups, that is methyl, hydroxyl, ethyl group, and this hydrogen, these will be given priorities, right? And what are these priorities would be like 1, 2, 3, 4, or you can simply give the priorities with alphabets like A, B, and C, D according to now why, what are these priorities, what does that mean? It simply means that you will give the priorities by looking at the atomic numbers of these 4 atoms that are directly attached to this stereogenic carbon, right? You are going to look for the atomic numbers. What you are going to look for? You are going to look for the atomic numbers of the atoms that are directly connected to this stereogenic carbon atom, this one, the stereogenic carbon atom. So you are going to look for the atomic numbers of oxygen, then hydrogen, then of course this carbon and like this. So let's check the atomic numbers. Now, as you know that carbon has got 6, hydrogen has 1, oxygen has 8 atomic numbers. So these are the atomic numbers basically. So now what we are going to do, that we are going to give the priorities like wise atom with the highest atomic number would be given as top priority. Atom with the highest atomic number will be given the top priority, right? That is 1 would be given. So here now, if you look here around here at this carbon, at this structure, oxygen, if you look here now, oxygen has 8, that is, it has got the highest priority, right? So now according to our rule, we are going to give this number 1. This would be given number 1 priority. Number 1, as oxygen is at the top priority. It is the atom that is directly connected to your stereogenic center, stereogenic carbon atom or a stereogenic center. So now as oxygen in our case is has the highest priority, so whereas now we will look for the lowest priority group. Which is the lowest priority group? That is directly attached to our carbon atom, of course the hydrogen atom here. So hydrogen has 1, right? So we are going to give it 1, 2, 3, 4. So which one? 4th priority. It will be given number 4. This hydrogen will be given number 4. After giving the priority, that is the highest priority to the oxygen and to the lowest priority, now we have the other 2 groups, that is this methyl and ethyl group. Now we have to find out that to give priorities, which priority would be given to the next set of atoms. Now what is happening here, that here the carbon that is attached directly to this this group, that is methyl group, is again a carbon. And in that ethyl case, this case, again, there is again this stereogenic carbon is attached to a carbon. So this stereogenic carbon is attached to, both the groups via these carbons, right? Both are carbons. So now how to assign the priority? This is a question, right? How to assign the priority? So now as for both these groups, priority cannot be given as both the atoms that are directly connected to the stereogenic carbon are the carbons. Stereogenic carbon are the carbons. This is a carbon and this is a carbon that is attached to this stereogenic carbon, right? So in that case, what we are going to do, that we are going to see then or judge the next set of atoms. When this is happening, we have to check for the next set of atoms, that what are the next set of atoms. So in the methyl case, the next set of atoms is hydrogens, that is HHH, right? So now, as I just said, that the next set of atoms would be considered, and the process is continued till we reach the final stage. Now remember, priority is assigned at the first point of difference. That is, the first point of difference you will find out, the priority will be given to that. Now here, what could be the first point of difference? Now in the case of methyl group, you can see that it is attached to 3 hydrogens. The next set of atoms is 3 hydrogens, right? Whereas let's examine the enantiomer. Okay, now if you look at the model, you can simply see here how clearly it is seen that this stereogenic carbon, now here, where is the stereogenic carbon? Of course, this is the stereogenic carbon, right, at which these 4 groups are attached: the methyl, the OH, the hydrogen, and the ethyl group, that is this one, the ethyl group, right? So now what is happening here, as we have given up till now, we have given the priorities, that is the top priority to the oxygen that is directly attached to this stereogenic carbon, and the lowest priority that is 4 is given to this one, right? That is this one that has the lowest atomic number. That is it has got 1, so it will be given the lowest priority, that is 4, and this would be given number 1 according to our atomic numbers, because we have to move with the atomic numbers. Now the next set our atoms are, of course, the groups are this methyl group and this ethyl group. Now here again there is a carbon, and again this stereogenic carbon is attached to a carbon. So now the point of difference is that now we have to check the next set of atoms. The next set of atoms are these 3 hydrogens. These, in case of this methyl group, these 3 hydrogens. Whereas here in this case, the next set is carbon and 2 hydrogens, right? CHH. Whereas in this case it is HHHH. In this case of methyl, the next set of atoms is 3 hydrogens. Whereas here you can see in the case of ethyl, the next set of atoms is CHH. So carbon has, again, if you simply compare both, carbon has the higher atomic number as compared to the hydrogens, because we are now looking for the next set of atoms. So look for the atomic numbers of the next set of atoms. So according to this, the methyl group, simply the methyl group, it has simply what set of atoms? H, H, and H. These are the next set of atoms for this methyl group. Whereas if you look for the ethyl group, it has the next set of atoms like C, H, and H. So now if you compare both these, you will simply see that carbon has the higher atomic number as compared to the hydrogens, right? So what will happen? We give the priority. So ethyl would be given the next priority. That is the it would be given. This group would be given the next priority, that is 2, right? that is 2, it would be given, because you cannot give priority to methyl group because it has got all these 3 hydrogens, the next set of atoms. We will look for the next set of atoms. The next set of atoms are here for the case of methyl. These are the 3 hydrogens which has lower atomic number as compared to the ethyl group that is attached to this stereogenic carbon, right? So this stereogenic carbon has an ethyl group with the 2 hydrogens over here and 3 methyl groups here. So now what is happening simply that yes, you will simply give it, the next set of atoms is CHH, as C has the higher atomic number as compared to these hydrogens. So the ethyl group, that is this group, will be given the, second priority, right? First priority was given to OH due to oxygen at a highest atomic number, and lowest was given to the hydrogen, this one, right, as it has 1 atomic number. And now the third or second priority will be given to this. Now only the third one is left. So let's check out for that. So methyl will be given the third priority. Now we have all, so this methyl group will be given the third number, that is the third priority is given to this one, right? As I've just said that you can compare here the 2 groups. The priorities will be now set up according to the next to the next set of atoms by their atomic numbers. So if you compare these 2 atomic numbers, you will simply see that these hydrogens, this methyl group, that is this methyl group, that is over here, this methyl group, it has the 3 hydrogens over it, whereas here this ethyl, it has 1 carbon, and the next set of atoms has 1 carbon and 2 hydrogens. So it will be, ethyl will be given the next priority, and the last priority, the second last priority will be given to methyl group, that is this one. So it would be given number 3. So now the first priority according to our model and according to our this figure, you can simply see it's given to oxygen, that is number 1, and the lowest priority is given to, of course, the hydrogen, that is this one, right, this hydrogen. And then of course by looking at comparing the next set of atoms, the next priority was given to the ethyl group, and then of course the methyl group is given the third priority, which you can see according to our, if you look at the our model, you can simply see here easily how they are connected and how the priorities are given to the groups that are attached to the stereogenic carbon. This is the stereogenic carbon and the hydrogen, right? So the viewer is looking now from here. We are the viewers and we are looking now towards here, and we can see the hydrogen is pointing towards ourselves. Now if we rotate the molecule and if we simply see that the lowest priority group will be at the back side, it should not be confronting the viewer, right? If we rotate it in such a way that the lowest priority group should move at the back, so what it would be like, let's see. So now let's rotate the molecule to push the lowest priority group at the back, right? So in that sense, what is going to happen now? Here you can simply see that I have vanished the group that was troubling us. That was the lowest priority group. So what was that group? That was this hydrogen. This was the lowest. So we have rotated the molecule in such a way that now you can simply see the stereogenic carbon and a methyl group and an OH group, and of course the ethyl group, that is this one. This is an ethyl group. So now you simply are now going to see that you can't see the hydrogen because it is at the back. Now it is at the back. Now viewer is looking it like this. Now so the lowest priority group, that is the hydrogen, is now away from us, or is simply, you can simply say that the lowest priority group is directed away from the viewer, from us. Now you can trace the path now from, of course, from 1 to simply 4, 1 2 3 4, right? Now you will trace the path. How you're going to trace the path? As we do this, the direction of our finger or with a pencil or with this pen is clockwise. Now you can simply see how this is happening. This is number 1. This was number 1. Then of course the ethyl group, the arrow will be towards this, that is ethyl group. Then the arrow will be towards the methyl group, that is number 1, number 2 and number 3, right? So what is this direction? This direction is simply clockwise. It is simply, the direction is clockwise, right? As you can, we are moving according to the priorities we have given, that is number 1, then of course number 2 and number 3. So what is the direction of the arrows? This one, that is of course the this is simply the enantiomer is moving clockwise, so the enantiomer is designated as R. How it is designated as R? Simply because it is clockwise, so it would be designated as R. Whereas it would be counterclockwise if the and it would be called as, the otherwise is would be designated as S. So this in our case it is clockwise, and you can simply call it R2-butanol. You will call this molecule R2. So you will call this molecule R2-butanol. Butanol. This would be the name of our compound, which is this, that is R2-butanol. Now if you simply draw the figure, I can draw it for you so that you can simply see how I have done it. This is the stereogenic carbon. If suppose this is the stereogenic carbon, this is the methyl group, right? And this is of course the oxygen and hydrogen, that is a hydroxyl group. And this is, if this is CH2 CH3 ethyl group. And of course the one that is away from the viewer, if the viewer is from this side, if the viewer is watching from this side, right, this is the eye of a viewer, right? If he's watching from this side, right, so this is viewer, what he is going to see that this group, that is the lowest priority group, is at the back, right? Whereas he is confronting these 3 groups. Now according to our statement, the direction of arrows would be like this, right? That is number 1, number 2 and then of course number 3, right? It's simple, and this is clockwise, and will be designated as R because it is clockwise. Because here what is happening, the arrows are clockwise, And why they are clockwise? Because we move according to the priorities we have assigned to these 3 groups, that is the hydroxyl and these ethyl group and then the methyl group, right? And this is the 4th group that is at the back, which we are not looking for right now because that is the lowest priority group. So in this way we can simply assign the R and S designations to our enantiomers, right? Now the R is for the rectus and this S is for Sinister. Now S is not in our case it's not S right now, it's the rectus R2-butanol because it is clockwise, and if the case would be reversed then it would be S, right? S2-butanol, and that would be counterclockwise or anti-clockwise. The direction of arrows would be different, right? They would be opposite, so that would be anti-clockwise. If the directions are this way, that means it's anti-clockwise. But here the direction is like this, right? The direction was like this, that is from this to this. Simply you can see from this to this, right, to ethyl group, and then from ethyl to the methyl group. So this was the direction, right? This was the direction of our priorities which we have given, and the direction of the arrows, that is the arrows from here to here, and from here to here, right? In this way, you can designate R and S designations to any of your enantiomers, right? This is the way how you can do the, you can study the nomenclature. This is the, nomenclature that was suggested, by the three very renowned scientists, that is Gahn, Ingold, and Prelog. And at in the year 1966, they have developed this this sequence rules, or you can say they find out the way to designate the configuration of simply the stereogenic carbon atom, right? The tetrahedral carbon atom or a stereogenic carbon atom. So these were the three scientists, Gahn, Ingold, and Prelog. These were the three scientists. So this was was the system that permit us to make an R or S designations to any of the compounds that contains single bonds, right? Whereas the other compounds that contain multiple bonds, other rules are necessary. So we will study that afterwards. Right now, this was the first 4 or 5 rules which I thought that I must share, and I must show you how to give 2-butanol the designation as R2-butanol, right? So today our goal is achieved, as you have seen the model also, how the arrows moved and how we have given the priorities according to the atomic numbers. I hope you like this video. You will share with your friends and you will enjoy it. Thank you very much. Now, up till now, we were discussing about the, enantiomers or giving designations to R and S-like designations to the groups that are connected to each other by single bonds. Now, what happens if the groups are simply containing double or triple bonds between them? How we are going to assign the priorities? As, if both the atoms, what we are going to do? If we will simply duplicate or triplicate them, right? How we are going to do that? We're simply going to do it like that. You can see C, double bond, Y. If this is a case, for example, so it would be like how? You're going to duplicate it. Y. And then, of course, C. This is how you will duplicate it. And simply, if it's the compound is like, it has a triple bond, what you are going to do, how you will write C, Y. This is how you're going to now C, and then of course C, and then of course here Y. This is, you are simply going to give them, duplicate, they will be duplicated or they would be triplicated. Now the symbols in these parentheses are simply what these are. These are duplicates or triplicates, right? These parentheses, right? So that is simply what the atoms that are at the end of these bonds, that are multiple bonds, that is double and triple bonds. Now, for example, the vinyl group, if you look at the vinyl group, CH, triple bond, CH, double bond, CH2. Now, this is of higher priority. It would be of higher priority as compared to, would be of higher priority then of course isopropyl group, that is this one, CH, CH3 and 2. Why? Now I just tell you why. Let me clean this. So this would be treated as CH double bond CH2 is be like simply C of course a hydrogen over here, then C, a hydrogen here, and of course an H and a C, right? This would be like this, which is then again of, it is of, I mean this is the same group, this is the higher priority, which is higher priority group. Then which one? I'm going to make it more clear for you. CH, if you just open the compound so that you can simply see more clearly how the connectivities are and why we are giving them this, C and then H, H and H. Now the priorities, why the priorities were set up like this. Now this has the higher priority as compared to this one, that is vinyl group. It has the higher priority as compared to the isopropyl group, that is the isopropyl group. Vinyl has the higher priority. Now why? Because now look at the second set of atoms out here. So the second set of atoms out at the vinyl group, see the following structure would be like, so I mean for vinyl group it would be like C, and of course it would be like CH and H, right? CH and H. Whereas for isopropyl, as I've just said that now we will look for the second set of atoms, the vinyl group. Now vinyl group simply it has this connectivity CH, whereas the isopropyl group would be like H, H and H, right? So now as we have just because now why this is happening, because of course the first set of atoms, first set of both the groups are the same, that is CCH. The first set of atoms, both have same connectivities, that is what were that C, it were like C, C and H. It was like C, C and H. Both have the same connectivities, right? So we look for the next set of atoms. So in that sense, the vinyl group was designated as the higher in priority as compared to the isopropyl group, that is CH, H is greater than H, H and H, right? That is vinyl group, and that is isopropyl group, So this was another very interesting and simple way to follow. This is it. You can simply see here, vinyl group has the higher priority as compared to the isopropyl group when we are discussing the the duplicates or triplicates of our if the compound has double and triple bondings, how we are going to deal with it. So this is how you are going to do it. There are other rules also. There are other rules also for the more complicated structures, but for the beginners level, for the initial ones, this much knowledge is more than enough. That how you will deal with the single bonded molecules and how you are going to deal with the the double bond and multiple bonded compounds, right? So this was something very interesting. I thought you must have enjoyed this video, and you will learn from this video, and you will share and discuss with your friends how to assign R&S designations to such compounds, right? And to compounds that contain carbon-carbon single bonds when they have the stereogenic centers and they are bonded singly, whereas to other four groups, whereas when they have the other when they have the multiple bonds, how they are dealing with it. Now you will have the command. Now you can simply share with your friends more easily. I hope you find this video interesting, and this molecule also very interesting and very beautiful. I simply like them because I made them and I prepared them, I study them, so that makes me follow all the this connectivities nicely, and I can see them easily how they are attached, and how a stereogenic at center or a stereogenic carbon atom is identified, and how the 4 different atoms are simply shown and connected here to this stereogenic carbon, and how visibly it is clear that what is a stereocenter, what is a stereogenic center or a stereocenter, right? So this gives us a lot of great knowledge. And now today's video conveyed you a lot of things about the simple structures, the single bonded structures, and then of course how you're going to simply duplicate and triplicate the atoms, and you will simply get and you will assign the priorities as I've just mentioned here. So let's hope and meet in another video with something more interesting, maybe some sort of different other topics which are parts of stereochemistry and are related to your topics that you are going to study in your master's and in your graduate and your undergraduate and graduate levels and your master's level. Thank you very much.